Or good afternoon, everybody. It's my great pleasure to introduce Professor Larry Girolamo. And Larry is a blue waters professor in atmospheric science at the University of Illinois, Urbana campaign. And I have known Larry for quite a few years now, in part because we both are on the NASA's multiple angle imager for aerosols called Maya mission. That was selected by NASA in, I think in 2016, and we are planning to launch it in the next couple of years, likely in 2022 or 2023. And certainly Larry is an expert in multiple angle imaging techniques. And he also is a co-I of MISR imager on Terra satellite. The MISR on Terra was launched in 1999. And prior to that, he actually participated in the formulation of the MISR satellite mission. So he's in some ways he's a veteran in satellite missions. And not only that, he's also expert in 3D radio transfer and have used the MISR and other satellite data, such as MODIS, to study aerosols and the clouds. And so we now have more collaborations on the Maya team. And today, he also lead a lot of field campaigns, primarily focused on the physical side of the aerosols and the clouds and the weather and the climate change. So today he's going to talk about the spatial heterogeneity issues in the passive remote sensing of cloud droplets. Larry, thanks for coming. The floor is yours.
Thanks, Jun, and thanks for having me here. I had a great morning talking with so many of you. I really enjoyed it. Now, so today I am going to talk about confronting spatial heterogeneity issues in passive satellite remote sensing of cloud properties. But I know a lot of you are actually aerosol folks, and we could have easily swapped out the word cloud here for aerosols, since much of the issues that we face in remote sensing cloud properties are very similar to issues we face in remote sensing aerosol properties. And of course, then there's all the cloud aerosol interactions. And if you are working in that domain and using cloud products from MODIS or MISR or other instruments, this talk will also be very relevant for that line of research. So by spatial heterogeneity, I give an example right here up front. As we look at this scene, we're over the Philippines. That's the green land that you see down there. Those are the Philippines. And you see a lot of clouds. And the world is a very, very cloudy place. And you could make out wonderful spatial structures that we have here, not just of high clouds, but also low clouds. Many different there are mesoscale phenomena that are in here that are evident, both from fairly small ones to more moderate and to much bigger ones as well. The other thing you'll point out that when I talk about spatial heterogeneity, I'm not just talking about the horizontal dimension as we see here in this image, but if you have experience in looking at satellite data, you also know that in here, in this image, there's a lot of multi-layered clouds as well. So we have to deal with vertical spatial heterogeneity as well. Why can I no longer move forward? There we go. All right, so just a brief outline of the talk here. I'll provide you with some background, and then I'm going to dive into a number of cloud products, the cloud fraction, cloud top height, cloud drop effective radius. I'll discuss a NASA field campaign that I just got back from, and then provide some concluding results. I'm going to center the discussion around three separate papers that came out recently from my group. I know you may think I'm crazy to present so many papers in one presentation, but of course, I'm not going to provide any details. It's really just a storytelling that I'm about to present. I'd like to acknowledge my funding agency, NASA, and the 3 key students here that have helped me out in developing these papers. It's largely their work I'm presenting here. All right, so clouds, we know, interact with all components of the climate system, more or less. This includes radiation, right? Clouds are the largest modulator of radiation on our planet. They're a key component to the hydrological cycle. They have an important role in atmospheric chemistry, including, right, the photochemistry, since the clouds modulate the radiation field, and so on. This interaction, as you all know, is very complex and difficult to capture in our general circulation models. And, you know, really, you hear the same story now, but the story began a long, long time ago about this difficulty of putting clouds in climate models. And here I just point out the so-called Charney report, which dates back to 1979, which kind of predates all the IPCC stuff. But the conclusions are back then are basically the same now, and that is, you know, it must be emphasized that the modeling of clouds is one of the weakest parts of the general circulation modeling efforts. Now, there's not just modeling. We have to recognize that as they did back then, that there's an insufficient quality in our cloud observations for validating models. Now, back then, there was very little satellite data they had to go by. We have a lot more of that now. But as you'll learn throughout my talk, we still have a long way to go in terms of having cloud observations that are sufficiently good enough for assessing climate models, and certainly not good enough for assessing climate change, not yet. So there's a lot of work left to do, and that's basically how I will end the talk. So with the release of this report, it provided motivation to launch the International Satellite Cloud Climatology Project. So it was born in the early 80s, and its job was to piece together weather satellites from around the world to produce a uniform cloud climatology from space. The first data release came in 1991. The project remains healthy. But piecing together weather satellites, while good, is not necessarily great. They got very poor calibration. So NASA got in the game in the mid 1980s with a mission that they called Mission to Planet Earth. And from that, the Earth Observing System was born. And from that, the Terra satellite became the flagship satellite of the mission to planet Earth. So Terra was launched in 1999 in a 10:30 a.m. equator crossing time orbit. That orbit has been largely stable by plus or minus 1 minute for much of the mission. This is the longest single satellite stable equator crossing time satellite record for many geophysical products, including clouds. Because it's our longest, most stable, it's also our most valuable for climate research. So MODIS, I'm sure you all know this, MODIS is a wide swath imager with 36 spectral channels from 250 meters to 1 kilometer resolution. MISR is a multi-angle imaging spectral radiometer. As you could see here in this, what we're trying to depict is the 9 separate cameras viewing from 70 degrees in the backward direction to 70 degrees in the forward direction. And then there's Aster as well, which measures down to 15-meter resolution, but over a narrow swath. So let's keep that in mind, that we have Aster, MISR, and MODIS viewing the Earth simultaneously and with coincidence. And that becomes a valuable tool when you have data collected at the same time in regions. So this data from Terra and Aqua and other satellites are heavily used in climate assessments, such as the IPCC report. So we see here, if we just take a look at this particular component of the IPCC report in Chapter 7, while dealing with cloud aerosol interactions. I'm sure you've seen this all, but I just want to point to you that in our assessments of cloud aerosol interaction, we have largely the MODIS data is part of that. And they bring in the cloud products to do these analyses. And the products that we talk about are the cloud fraction, the cloud top height, the cloud optical depth, cloud drop effective radius. These are things that we retrieve from instruments like MODIS. So they're in widespread use and have direct application in assessing our climate. Now, when we think about the climate and ask, well, what are the models predicting? The models are predicting that with warming, with CO2 rising, we're going to end up with a warmer climate which will lead to rising high clouds, broadening of the Hadley cell. There'll be less low clouds in the mid latitudes. There'll be more polar clouds, or at least thicker polar clouds, and so on, and a poleward shift in the storm tracks. So we're looking at change now. So we're looking at changes within this picture. We see cloud tops, cloud cover, cloud optical depth all being called out on. And with Terra being our longest record, if we're going to observe change, Terra is our best record to do that because of its longevity and stable equator crossing time, which is key. There we go. So one of the questions that we try to address early on is, well, how well do we need to measure cloud properties in order to address some of these climate questions and climate observations that we expect to occur in a warming climate? And the answer has been assessed in multiple places. And here's what we just refer to as the O-ring report, which basically says, look, if we're going to produce a climate data set, and these are the variables we want, cloud cover we should be getting accuracies of about 0.01 with a stability per decade, right? So if you want to monitor how things are changing, the changes that are predicted by the climate models are pretty tiny. The signals are small, so you need really good stability in your products. So that's been assessed to be down here at 0.003 in terms of cloud fraction. Cloud drop effective radius, we should be about 10%, which is about 1 micron. And then for cloud top height, it's about 150 meters. There have been a number of independent type studies that try to lay out the requirement. This is the O-ring one. It's the first that I'm really aware of that did a good job. And then there's a more recent one is from the WMO in their global observing system, basically saying roughly the same thing that the O-ring report has said. So this got us wondering, okay, well, are we meeting that with our current sensors? So back in 2005, GWEX, the GWEX program launched the Cloud Assessment Working Group, which I'm part of. And this involved 11 satellite teams around the world who produce public products that have been validated. So these were some of the requirements, got to be validated, and it needs to be public and needs to be in widespread use. So this, we settled in on 11 products to assess. They are listed here, everything from ISKIP to AVHR Patmos X, to the MODIS, to the Calypso, Polder, Miser, and ATSR. And when we take a look at what our assessment report finds is that there's broad agreement in terms of the variability in clouds that we see, but the differences amongst them are still quite large. Here, even in the zonal mean, you could see here the details aren't important in terms of the instruments, but all I want to point to is that there's a substantial spread in here, being smallest at mid latitudes with at the downwelling branch of the Hadley cell, somewhere around 0.07 in terms of cloud cover, all the way to polar latitudes where the spread is upwards of 0.5 or so. So, if we, in as much as one could say, the spread amongst them is some indication of accuracy, then we're very, very far away from meeting any sort of climate requirement in our data set. And that is actually concluded in the GWEX report, that we're not doing good enough. even though we've learned a lot from these data sets. And that's highlighted in that GWEX report. Now, looking at things, looking at 4 of those data sets more closely, we have the ISKIP, the Calypso, MODIS, and Miser cloud cover product. And this is total cloud cover for 2007. And here again, you could just use your eye and you could actually see large differences amongst instruments in different regions of the world. In some places as high as 0.4 difference in cloud cover. So it's substantial. And our understanding of why this is the case is good. It really is. We understand that there are resolution effects and view angle effects. There are issues dealing with diurnal sampling, right? Miser's sampling at 10:30 a.m., Calypso sampling at 1:30 p.m., these types of things. There's instrument sensitivity and methodology effects that come into play as well. For example, Calypso is a LiDAR, so it's very, very sensitive at detecting very thin clouds. So we should expect it to be able to detect more clouds just because it's more sensitive to thinner clouds. What I'm going to just dive a little bit into is the resolution effect. Okay. So to explain the resolution effect here, imagine I have these cubic cumulus cloud field here, and I want to measure the cloud fraction. And the way we measure cloud fraction, so let's say I have an imager. Let's say we're looking at a region that's 8 pixels by 8 pixels large. And we just simply count up the number of cloudy pixels divided by the total number of pixels, and that gives us our cloud fraction. So in this case, we have 9/64, so it's 0.14 cloud fraction. But if I actually move the grid a little over, and I now go ahead and count the number of cloudy pixels that have some clouds in them, well, then I end up with a cloud fraction of 56%. So we've gone from 0.14 to 0.56 in cloud fraction in this very simple toy experiment. It really isn't a toy experiment. When we go out in the field and we actually look at a lot of satellite data, both at coarse resolution and at high resolution, and in particular when we bring them together to do the comparison, it really shows up as being a very, very popular thing, the sheer number of subpixel clouds that are out there. So here's an example of the Miser cloud mask at 1.1 kilometer resolution. It's shown here in yellow, and it's overlaid on the Aster 15-meter visible radiance. And you can see pretty clearly all these subpixel clouds that exists within the Miser cloud cover. So surely Miser here would greatly overestimate the cloud fraction relative to what we would measure from Aster at 15-meter resolution. Now, I studied this actually a very long time ago as we were getting ready for the Miser mission and we were to be developing our cloud products, including cloud cover. I wanted to get an assessment of what that error would be due to these resolution effects. So the paper actually outlines it's actually a mathematical treatise on bounding the error in these situations. And as you would expect, it not only depends on the pixel size and cloud size and the details of the algorithm, but it also depends on the spatial distributions of the cloud. And because of that spatial distribution, you could get the error characteristics are actually become difficult to model. So at that time in that paper, not only do I provide the mathematics of the error bounds that we should expect, I also provide a solution to help correct estimates of cloud fraction. And it was basically a pattern recognition machine learning approach where if you have coarse resolution data and you have some training data that brings in fine resolution as well, then you could train a model based using the high resolution data acting on the coarse resolution data to produce a resolution corrected cloud fraction. Now in 1997, we just didn't have co-located coarse resolution and high resolution data available. So all my work back then was on synthetic data. But with the launch of Terra, where we have MODIS, MISER, Aster, all looking at the same region at the same time, we have loads now of high resolution data that's co-located with the coarse resolution data. And a student of mine, Ali Jones, back in 2012, demonstrated using this pattern recognition approach applied to MISER and Aster, using this Aster training set that we developed. It was only over ocean, but it was pretty extensive. And what she showed is that, you could get unbiased estimates of cloud cover this way, which we thought was great. So we ended up applying the algorithm to MISER operationally, and now we have 2 decades of resolution corrected cloud fraction. So I finally got a student who was willing to look at it. And she did that, and she published a paper recently in GRL on the performance of the resolution corrected cloud fractions from MISER. So and this is basically the key takeaway from her paper is right here. So if we look here at the right, we start off with the original MISER global cloud cover. So this is an 18-year climatology segregated by season. In the middle is the MODIS cloud climatology, and here it's been sampled within the MISER swath, so there are no sampling difference between the two. So we can see that MISER is cloud overall, tends to be, most places tends to be cloudier than MODIS. And on the left here is the resolution corrected MISER cloud cover. And what you see is actually remarkable. The correction is massive, right? Notice it's not a blanket correction, everywhere. There is strong spatial dependence in the amount of correction that's done. And it's pretty clear that in regions of the world where we have trade cumulus dominating the total cloud fraction, this tends to be where we have the largest corrections. So, whereas in the stratocumulus regions of the world, there's much less correction as you would expect. So she ends up concluding that, between 50 north and 50 south, this is where we apply the correction algorithm, the cloud cover drops from 0.65 to 0.47, which is massive. And in fact, we were all a little bit shocked that it could be this large. So we thought, okay, how do we go ahead and validate this? And it's actually fairly easy. We have all this high resolution Aster images, and we could just go out and grab a whole bunch of random samples and look to see how we're doing. And here's an example of that. And what we've done is we went ahead and we chose a number of places around the world where things seem to be really bad, meaning where the resolution correction was largest. So here are the 6 regions around the world, and we grabbed 180 scenes from Aster, which we thought was, we did some calculations show that it was enough scenes, because it's manually intensive, right, to do these comparisons with Aster. It's quite involved. So we randomly chose 180 scenes and computed from Aster and computed the Aster cloud fractions. They're segregated here by land versus ocean, and you can see in the histogram here of the indicating the average cloud fraction for region 1, for region 2, for region 4 and 6 over land. We see that the Aster cloud fraction, given in blue, over land is larger than the resolution corrected ones, but not so over ocean. The resolution corrected cloud fractions in red are within about 0.08 of the Aster cloud fractions, which still sounds fairly large, but when you consider what MODIS and MISER were indicating in these 180 scenes, we had MISER and MODIS in yellow and green really overestimating on average about 0.4 to 0.5. So huge values of cloud cover. And as soon as we looked at the images, as we did here, right, we see, oh my God, yeah, there's the overestimate is clear. So this is something we're going to have to contend with. And interestingly enough, the global climate models, many of them were saying, the world, that the satellite records are too cloudy, and they may have been right. Now, it does go at odds with what I showed in my 97 paper and what Ali showed in her 2012 paper, and that is we should be able to get unbiased estimates of cloud fraction, and we're not. We still have this biases in some regions of the world up to 0.08. And we're essentially positive it's because the training set that we used is not adequate. It really only represented a couple of regions, sorry, 3 regions of the world. The Gulf of Mexico, the tropical Western Atlantic, and part of the Indian Ocean. So the next job for us is to actually expand our training set and redo the whole exercise to do better. Now, it's not just miser. So here you could see the trade cumulus. I'm back to the uncorrected version here. The cloud fractions are still very large in the trade cumulus regions of the world, as you can see here. But notice Calypso 2 has the same issue. It's not just, as we looked into the Calypso, it's not just its ability to detect thinner clouds that's leading to higher cloud fractions. It's also the fact that its cloud product is at, 5-kilometer resolution or so. So very coarse resolution. So it has a very large resolution effect, large resolution bias in its cloud cover estimates that are buried in that product. So if we take the next logical step, and that is, well, how does the cloud cover vary with altitude? Right, so we use the usual ISCIP designation for high altitude cloud, mid altitude clouds, and low altitude clouds, shown here. And here we're looking at miser, MODIS, ISCIP, and Calypso products. And what you see should be pretty remarkable, right? These are public products. When we go out there and you could go grab this data yourself, and take a look at it, and this is what's used in other studies. And it's a bit shocking, right? If you take a look at just the fraction of high clouds, of course, we have Calypso being more sensitive to thin clouds, detecting a whole bunch relative to ISCIP, MODIS, and especially miser. Miser has the lowest high cloud fraction of all of these instruments. If we go down in altitude to mid-level clouds, you could see that Calypso doesn't think there's very much mid-level clouds. Same with miser. Miser doesn't detect much mid-level clouds. But there's a whole bunch of them in the ISCIP and MODIS data sets. And when it comes to low clouds, clearly miser has by far the most low clouds in its data set. And the reason why this looks the way it does is because there's vertical heterogeneity involved. And the hypothesis kind of looks like this, right? You have the LiDAR, which is very sensitive to detecting the cloud, thin clouds. So there's a lot of thin clouds up there. So it has a lot of high clouds then it detects. MODIS, being an IR technique, is sensitive to emissions from both the cirrus and the low clouds. So you often get something in between then. And then miser, which uses a stereoscopic technique to retrieving cloud top heights. If the cloud is thin enough, then a stereo technique keys in on texture, right? So if the lower cloud is providing much of the texture that you see in the images, then it will be the low cloud heights that it detects. So miser, in some sense, when there's thin clouds present, will see through the cloud to retrieve the altitude of the low cloud. So this suggests that, when we're looking here, that there's a lot of thin clouds out there, and that there are a lot of low clouds that are not represented in all of the climatologies. Now, how do we go ahead and validate this? For Terra, doing any sort of global validation has been very, very difficult. The reason being is that we don't have an active sensor in space. The A-Train and MODIS on Aqua has had the advantage of having Calypso to do validation, but we didn't have that for Terra. But as many of you know, through our discussions earlier today, there's the CATS LiDAR on the International Space Station, operated for 33 months. So we thought we would use that. And that is the topic of Arkas Mitra's paper, which in my view is the most thorough assessment of any cloud top height product out there. So if you're interested in cloud top height, I think and understanding air characteristics of cloud top height, that's really the go-to paper. Right, so we went ahead and because of the it's on the International Space Station, right? So it's drifting with time in the diurnal cycle. We only catch it every now and then, but it turns out over 33 months we get a lot of collocation. And here by collocation I mean within a kilometer and within 5 minutes. And we get nearly 20,000 coincident points, plenty to do some statistics. Now, the best case scenario that we could expect is under single layered, optically thick, unbroken clouds as measured by CATS. And in those situations, what we find is that, as shown here, if we just take a look at the overall, we find that MISR is essentially twice as accurate and twice as precise compared to MODIS. These errors do depend on cloud type, and I'll show that a little more later, but even within this single layered optically thick unbroken clouds, it does depend on the height of the clouds. Needless to say, you'll see actually very little variability in MISR heights going across levels. The reason being, part of the reason being is that the entire MISR error budget is self-contained, it's fully traceable. So you could work out the math and work out what the error would be, and we were able to validate that error. So it's been great. MODIS, on the other hand, its error budget depends on the assumptions it makes, and it makes a number of assumptions in its retrieval algorithms. And whenever you deviate from the assumptions in nature, you end up with a systematic error in the retrievals. So it depends on these assumptions. It depends on external ancillary products. MISR doesn't. And for low clouds, by the way, it actually makes use of a latitudinally varying lapse rate that's been tuned to give the Calypso cloud top heights. So not surprising then, this low 60 meter bias that we see here is very small, and is in part due to this tuning to a LiDAR already, rather than any real, any physical retrieval. We could extend that to all clouds, as we did, and we find that it not only depends on the cloud top heights, it also depends on the optical thicknesses of the clouds, and it depends on situations of cloud overlap. And it's these regions where we have cloud overlap is where we have the largest errors. Now, as you can imagine, if you go back to that plot, here it is. As you can imagine, if the upper level cloud is very thin, you have MODIS also detecting down low. You have MISR seeing through it, detecting the clouds down low. But if it's thin, the LiDAR will also see through this cloud and see the lower cloud as well. So it'll detect the two layers in this example. At which point we make use of we also make use of a closest CATS layer approach. And what we find when you do the closest CATS layer approach is that for MODIS, those low cloud biases are about what they were for the thick clouds. And we also find that the presence of the thin cirrus doesn't impede the uncertainty in the retrieval of the low cloud height. Other things that we've learned in the study is that how thin does this cloud need to be before we're always detecting low clouds? There, the optical depth is about 0.4. And then we also discovered a new effect that has not been reported on before. And that is what we've been calling now the cloud top height stereo opacity bias. Because MISR has a fantastic error budget formulation, whenever our validation, as we're doing here, comparing against the LiDAR, doesn't match up, we're actually able to say why. And in this particular case, as you can imagine, in order to get contrast, it's not going to happen on the first few cloud droplets on the outer boundary of the cloud. The contrast actually emerges from somewhere deeper in the cloud, right? And how deep in the cloud does that contrast emerge? Well, depending on the cloud type, it's somewhere between -60 to something like 60 meter to 260 meter within the cloud, from the cloud top. So that's something important to keep in mind for future designs of stereo imaging systems. You could work out the math all you want on the error budget and design a really good system, but you're always going to have the stereo opacity bias to contend with. So let me move on to go back to the GWEX cloud assessment database that was developed, and let's take a look at a different cloud product. Here we'll look at the liquid cloud phase cloud drop effective radius. Again, these are public products. I'm not doing anything fancy here. I'm just taking a look at it as we did in the GWEX cloud assessment report, and you can see that you take MODIS, the PATMOS AVHRR, the ISKIP, find huge differences between them in our climatologies of cloud droplet effective radius. And remember, this is a cloud droplet effective radius is something that moves on, that we use to assess aerosol cloud interaction from space. What we also notice is this curious behavior. Notice here that the largest droplets seem to follow, have the seasonal effect, right? I'm sorry, this hemispheric effect. So in January, we have the largest droplets being in the northern hemisphere, and in July, those largest droplets are in the southern hemisphere. So that's a little odd, why that would happen. But needless to say, when we talk about climate data set requirements, and we're considering, well, what does the spread look like in our current climatologies? The spread is huge, right? And we're certainly nowhere near requirements that are put forth by climate scientists. So in case you're not familiar, the effective radius is defined as the third moment to the second moment of the drop size distribution. And it's retrieved with an instrument like MODIS or AVHRR using a so-called bispectral approach, or Nakajima-King approach, which simultaneously retrieves cloud optical depth and effective radius. It makes use of a non-absorbing channel where the droplets don't do any absorption or very little absorption, here at 0.86 microns. And then where droplets have a strong absorption, either at 2.1 microns, but we also have other spectral channels that we use, 1.6 microns or 3.7 microns. And the basic idea is you take a whole bunch of different cloud scenarios and you pre-compute lookup tables. So here's a graphical cross-section of the lookup table showing the 2.1 reflectance, 0.86 micron reflectance, along with what the effective radius and cloud optical depth values would be associated with those reflectances. So the idea is you go out and you make measurements at these two channels, and you go into your lookup table and you basically pick out what the effective radius and cloud drop, what the effective radius will be and the cloud optical depth. Now, in producing these lookup tables, assumptions are made, right? And one of the key assumptions is that the clouds look like this. Now, if you're looking at a blank screen, it's because that's what I'm showing you. It's a blank screen. And basically, the assumption that is made is that the clouds are horizontally homogeneous out to infinity, and that they are vertically homogeneous as well. Now, of course, we know clouds don't look like this. This seems to be a major assumption that is made. When you look at real clouds, right, you have all this wonderful texture, and that texture is there because there's shadows involved. There's cloud side illumination involved. There's leakage and channeling of photons taking place. there's all these 3D effects that come into play that may be impacting our retrievals. So just to be clear, here's when we refer to one-dimensional radiative transfer, and we're considering this cloud here that extends out to infinity in the horizontal direction. It's illuminated everywhere at the top. Notice in this case, when we refer to 1D radiative transfer, this means that the radiative transfer, the radiance field, varies only in the vertical direction. There is no horizontal variability. But the world is, of course, 3D, and there are these pathways like shadowing, cloud side illumination. There's leakage of photons out the sides of the clouds and so on. And all that changes the reflectances that impacts the reflectances that we measure from space. And there are good discussions on, if you're interested in the 3D radiative pathways, the Varney, these two studies down here are excellent, if you're interested in that. All right, so yeah, I look at an image, it looks like it's looks like there's textures out there. From a remote sensing point of view, we want to be able to understand whether when we look down from space, can we actually observe these departures from the homogeneous assumption? So here we take advantage of MISR. Because MISR samples the angular distribution of the radiation field, we could ask, well, how often does the angular distribution of the radiation field match a plane parallel solution to within some tolerance level? And we've done that. And here's what that looks like. So here we're looking at the frequency in which the observed angular anisotropy of scattered sunlight is within 5% of a 1D solution, as measured by MISR. Basically, red means frequently 1D looking. Blue means infrequently 1D looking. And what you see is that, wow, there are some regions here that are red where it's frequently plane parallel. In fact, these regions, when you look into it, these occur whenever we're dealing with stratiform clouds under high sun condition. But in other places, when we're dealing with low sun conditions at 10:30 a.m., when we're dealing with heterogeneous clouds, it's just not, the angular distribution looks nothing like a plane parallel solution. You could also take a look at the spatial heterogeneity, where you simply take a local group of pixels, take the reflectances, compute the standard deviation, divide by the mean. So it gives you a measure of texture. So here I'm showing red down here. These red values have values near 0. So these are smooth clouds. Blue indicates rougher clouds, so more textured clouds. And this is the map that we get, right? So deviations from plane parallel, heterogeneous clouds. Deviation from plane parallel, heterogeneous clouds. So the two are clearly connected. And notice that it also, as I showed earlier in the RE product, follows the sun. Okay, so you end up with this kind of seasonal look to it, and that's because the solar zenith angle is changing. Now, is this important? Could this be impacting the science? Well, let's take a look at the Oreopoulos and Platnick paper from 2008, where they studied the relative cloud albedo susceptibility. So this is the susceptibility of the albedo A to a fractional change of the number concentration, N. Okay, and this is what they were able to back out of the MODIS record. So if you compare that to deviations from plane parallel, the two match up beautifully. Remember, whenever we deviate from an assumption, in this case, horizontally homogeneous, whenever we deviate from an assumption in a remote sensing algorithm, from what's actually out there in nature, it causes a systematic error. And this systematic error appears to be playing out in products like, or studies like looking at the cloud albedo susceptibility. Still, we could ask, well, is there evidence of that significant bias exists in the MODIS retrievals themselves? And the answer is yes. It's pretty easy to do an internal consistency test, what we call them, where this is the oldest one, where we take a look at the optical depth retrieval as a function of view and zenith angle. So here we're looking at a global mean liquid cloud only optical depth. Stratified by solar zenith angle, so from 30 degrees to 75 degrees solar zenith angle, and looking at that as a function of view angle. And of course, optical depth, by definition, there is no view angle dependence to it. It's the optical depth. It's the vertical integration of the extinction coefficient. So that doesn't make any sense. That shouldn't be there. You could also stratify the data another way. And here we did it by scattering angle. And we looked at it as a function of latitude. And here we're looking at deviations of the optical thickness from the mean for that latitude. So basically this broad thing that we see here going from blue values, which are low, to high values that are red. That's equivalent to looking here at nadir to more oblique angles in this other figure. But what we also see in here is the strange line artifact that comes down here in blue. And there's only one reason that thing exists, and that is because there's a bias in the effective radius of the that's retrieved from MODIS. And you could simulate this fairly easily. So for example, if we, here shown in green, we have a cloud of optical depth 8 that we're simulating. With a true RE of 10. Now, if you take a look at the retrieved optical depth as a function of scattering angle, there should be no dependence, and that's what we see here in our simulation. But whenever you introduce a bias, so for example, in red here, we go from 10 to 18 microns, and then we look at how the optical depth varies with scattering angle, you have this behavior that takes place right here at the cloud bow or rainbow. So we call it the rainbow dip. And it turns out that essentially explains, in fact, we're unable to come up with any other reason that could explain the existence of this rainbow dip. So it turns out you could go ahead and you could model this and you could develop regression coefficients where the amplitude of this rainbow dip that exists, you could use that amplitude to estimate the bias in RE. So Dongwei Fu, one of my students, went ahead and did that, developed a set of regression coefficients that allows us to do bias correction to the MODIS product based on this rainbow dip approach. And this is the bias that we get. So this is for the Terra record, by the way. So it's the MODIS RE at 2.1, as measured with the 2.1 micron channel. And it's a little shocking, right? If you take a look, right, so typically droplets are about 10 microns effective radius. What we're seeing here is that the bias can easily be as high as 10, even 12 microns in some regions of the world. So a factor of 2 difference of what we would think would be there. And that's a little bit shocking, given how widespread this data is used in cloud aerosol interaction. We should be concerned that biases this large that are spatially varying exist. And you could come back and say, all right, how do we know we're right? Well, we have some field campaign data that were done in the past. Most of those campaigns were done for stratiform clouds under high sun condition. For example, in this 2011 paper, they concluded that, yeah, there's about a 1 to 2 micron high bias in MODIS. Well, that's essentially what we got here with our bias correction. More recent paper out here wasn't really designed. It was a field campaign that really wasn't designed to do validation, but they tried to do it anyways. And they concluded in somewhere in the realm of 8 to 13 micron bias. So we thought we would go to the worst place in the world for the bias, that is, and have our own field campaign, in part dedicated to doing satellite validation work in heterogeneous environments. And this is the topic of the NASA CampX field campaign. And from that, we determined through some validation exercises that I'll show you in a minute, that yeah, we do get these high biases that are upwards of 14 microns. So far, we're kind of the bias correction that we have seems to be playing out in terms of validation from field work. So CampX here is the cloud aerosol monsoonal process Philippines experiment. It's basically a cloud aerosol interaction campaign, but it's also there to provide key calibration and validation data for satellite observations. We had it was a 2-aircraft mission. We had the Sally Ride from a different campaign joining us, and we had the Manila Observatory helping out as well. We focused a lot on coordinating with satellite overpasses. And in the interest of time, I will skip through some of this detail and actually spend just a few more minutes here finishing up. So on the P3 aircraft, we had a remote sensing instrument called a research scanning polarimeter. It's a multi-angle line scanner that as it flies along, it collects multi-angle images, 125 views, in fact, so it's high sampling rate, that we're able to piece together to provide multi-angle views of the same scene. And we're able to do a polarimetric retrieval of the drop size distribution. Now, RSP also has the 2 bispectral channels needed to do a MODIS-like retrieval as well. So we have these 2 independent techniques, the bispectral one, which we think is heavily contaminated by these 3D effects. And then there's the polarimetric approach, which basically goes to take the polarized reflectances, and we fit the supernumerary bows to the model, supernumerary bows in the model with those in the observations to do a retrieval. And the beauty about the polarimetric approach is that it's largely single scattered radiation that we're observing, so it's not very sensitive to these 3D effects. So let's just go through this one example tightly, and then I'll wrap up. What we're looking at here is a it's a MODIS RGB for one of the research flights, research flight 17, and you can see we're in a cumulus dominated region. Overlaid on that, these little dots of color that you see, that is MODIS RE that's been retrieved. So the first thing you notice is that, wow, there's very few MODIS RE retrievals. And that's right, there's all these other clouds, there's no retrievals, which makes you think about the representativeness of our cloud climatologies, right? We actually don't have all of the clouds represented in the right amounts. And that causes some serious issues for science. But anyways, here you see the flight track, plus or minus 90 minutes, that's overlaid on this, and it's colorized by altitude. And in this particular case, we also have an Aster image, and I have a blow up of that Aster image here in red. The yellow box outlines the 60 kilometer by 60 kilometer Aster image, and the red box is blown up over here to the right. And you can see all the wonderful small little cumulus clouds are out there. And overlaid on that is the MODIS retrievals, which clearly are impacted by within pixel variability. Down at the bottom here, you'll see some green dots. And the green dots are the RSP polarimetric retrievals. And you'll see some red dots, which is the RSP bispectral retrievals of RE. And you can see the difference between the red dots and the blue dot, the red dots and the green dots are something about 10 microns or so. Now we could go ahead and we have the airplane also flying in situ, making in situ measurements of the drop size distribution. So we get the RE from that. And we could see that over here on the far right, we see that the REs from in situ match up very well with the REs from the polarimetric retrievals. Not so for the bispectral retrievals. Interestingly, if you take the MODIS retrievals that are in this scene and compare it to the RSP bispectral retrieval, they too are, I suppose, comparable, but much higher than both in situ and polarimetric retrievals. We also do this as a function of height to make sure we're able to capture relationships. So here the pink dots that you see are the in situ observations, and the other colored dots are the polarimetric retrievals. And we see that they both capture RE as a function of cloud top height very well. Not so for the bispectral technique, right? They don't match at all. And MODIS doesn't capture this relationship as well, not even close. When we put it all together and we look at all the research flights, yeah, it's it pretty well says that MODIS is carrying in this region a bias of about somewhere in the 8 to 11 micron case, 8 to 11 micron or so. So anyways, high is the point. It's only field campaign. It's limited in sampling, so we can't say too much, but it's certainly high. So again, it looks like it's high. So just to wrap things up then, thanks for your patience. Sorry for going over time here, but just want to point out again, Terra is our longest, most stable single platform satellite record for cloud observations. The techniques it uses for cloud retrievals are common for many other satellite records. So it's not just the MODIS or MISR, it's AVHRR and so on as well. We've made advancements in understanding, quantifying, and correcting systematic errors that are in the record and that are caused by spatial heterogeneity, but we are still far from meeting any accuracy requirements for climate records. So there's a lot of work to do. And the way we're going to get there is only by developing better remote sensing technologies and remote sensing theories that account for spatial heterogeneity, 3D radiative transfer as a forward model rather than a 1D model. These are necessary things that we need to do. So hopefully this is being addressed in the next big mission that everybody's talking about, which is the Aerosol cloud precipitation mission that is currently being worked out in terms of design. So there's a lot of work left to do. I think there's some theories out there that could handle some of these issues, such as 3D cloud tomography. So hopefully we have some young students here and postdocs who are ready to take up the challenge and lead what needs to be done. Thank you.
Thanks. Well, let's give a round of applause for Larry for a very insightful talk. You can also click on the reactions there yeah. Thank you, Larry. Really very insightful and also illustrated very well. I really enjoyed it, and especially I enjoy the way you explain a complicated problem with a couple of cartoons. Illustrate like how the subscriptor clouds affects the retrievals.
Yeah.
These are very I really very enjoyed it. It's really you demonstrated very elegantly. That's
well, I have an aerosol version of this talk also.
Okay.
A lot of the issues are the same. Yeah.
Okay. Well, I'm going to stop the recording here and open the floor for discussion.